going to talk about the first decade of his work, mainly late 80s to late 90s. I met Russell when he was a student in Berkeley, and I was a postdoc there. Then I got to know him even better over the years, meeting in various places and writing various papers. And then he spent 5 years at the Institute, where I got to know him even better. Yeah, I know a lot about Russell. I have half an hour, so I'm not going to tell you much about the great qualities he has. I think that people, I don't see the audience, so I don't know who you are and what you know. But if you don't, you should know that Russell, if you look at the picture, is a lot of fun. He's really funny. You know, he's extremely wise, not just smart or fast, but extremely wise. He's caring of people to an amazing extent. He's extremely generous. He's really brave also. I don't mean in terms of going through difficult technical areas, but also in articulating unpopular opinions where somebody needs to say them. In general, he's extremely articulate. His English is amazing, and you should read his papers or listen to his lectures because it's extremely clear. In fact, his clarity of thinking and vision, I think, is unique. Yeah, but I mainly want to talk about, you know, his being impactful, the way he impacted our field. And I started looking at the papers, and I realized quickly enough that maybe I should restrict myself. So I'll restrict myself to the first decade of his work. And it's going to be very telegraphic. Even in the first decade, there are a lot of people, lots of papers, you know, which are seminal. And some papers may not be seminal, but I really like them and learned a lot from them. And I'll just give you a sketch of many of these, and you know, you pick up what you can, and the rest you can just go to the papers and read them. So, you know, maybe the title of the workshop at some point was Russell's famous 5-word view from this paper. I want to just tell you, you know, especially for the young ones, you know, that it was not clear that we have 5 words. Since Russell articulated that nothing much changed. Why 5? Well, you know, I think we are really good at TCS in, you know, putting structure on, you know, words, universes that don't look like they have much structure. And we understood this already from the start, from the NP completeness, where suddenly lots and lots of computational problems that look very different turned out to be equivalent once you put the right notions of reduction and completeness. And this was not at all clear when you got to average case complexity or cryptography. So first, why do we have at most 5 words? Somehow, why do lots and lots of cryptographic problems are actually related? It was not understood in the mid-80s. The mid-80s were, you know, I was in Berkeley, also was in Berkeley. It was the amazing, crazy days where lots and lots of impossible tasks were, you know, becoming possible under the, you know, some assumptions like one-way functions and public or trapdoor functions. And you know, it wasn't like understood what the relationship of these problems are. Maybe each of them is a separate world. And Russell was, you know, key to putting structure there. One paper with Mike Luby really showed that not only one-way functions imply many cryptographic primitives, I don't know, key exchange, secret exchange, throwing coins into a well, there are numerous problems, commitments. What they showed is that one-way function is also essential. They imply one-way functions. And developing the technology in particular, I want to mention one key notion they introduced, it's distributionally one-way function, namely a weaker assumption where it's hard only to generate a pre-image under the uniform distribution on pre-images. This is equivalent to a one-way function, and this was key for this paper and many later papers, which this really helped understanding minicrypt. To understand the heuristica and another primitive which looked much stronger was the pseudo-random generation. And in this amazing paper, they showed that it follows from one-way function, and a later paper with Hastad did it in the uniform case. Here also was a key definition of force entropy. So you have to understand, this is the level at which I'll describe the papers. You have to really, these are all amazing, and I learned, I was there and I learned so much from them. And the whole field learned a lot from this. And this really collapsed these worlds. Now, why do we have at least 5 worlds? Well, what separates these worlds? This, again, Russell was a key player there to understand that they are not all equivalent, not all problems. Key paper with Stephen Rudish showed a separation, really, between minicrypt and cryptomania under an oracle. Basically shows that there is no black box reduction from secret key agreement to one-way function. You cannot just do key exchange and public key encryption. Another separation, or related to understanding the relation between heuristica and pestilence, came in. So the background, whenever I show something in purple, it's a background. Levin in '84 came up with amazing, paper that defined average case hardness. Average case easiness, people knew that lots of problems are easy on average, but what about, sensible definition of hardness? This was a very mysterious paper, I should say, to me and to many others. In particular, because it dealt with a notion that was p-computable distributions. Then Russell wrote a paper with Levin that really explained everything. I mean, I think that how natural this definition was. In this paper, they showed that it's the same thing whether you look at this strange notion of Levin, not strange, but maybe not convenient definition of p-computable distributions, and show that just sampleable distributions are enough for this definition. And it did lots of things, as I said, simplify, clarify this definition of NP hardness on the average case. But it also showed that in the pestilent world of Russell, where it seems that, he says that it's the worst possible world. By the way, I'm referring to these worlds, I assume that you all know what they are. They show one positive consequence, one thing that's pretty nice in this weird world, pestilent, where we have no one-way functions, but there are hard on average problems. In this world, the one positive thing you can do, and it's far from trivial and follows from these ideas in this paper, is that it is possible to predict any efficient process. So if you regard natural processes, like things that happen in the world as, efficiently computable probabilistic processes, we can basically predict everything. This is if there are no one-way functions. Okay, let me continue. This was so we know why there are 5 worlds now. There are at least 5 and at most 5, like Russell said. Let me move to other, areas that he touched in these early years where things were unclear, and he just basically opened new doors to new worlds and to new areas. And I'm again going to telegraphically touch on some of them. One is communication complexity. Of course, the big field starting with Yao. And I want to, the background to one paper is this paper I wrote with Maurizio Karchmer, where we defined, we managed to express circuit depth in terms of communication complexity of a related problem. And it was about this conjecture that would imply, circuit low bounds. You just have to prove sort of a direct sum on communication complexity relations. It seems so elegant and so easy at the time. And moreover, it suggested something that didn't exist in the circuit complexity world because there were universal relations. And we suggested to start with proving direct sum theorems for universal relations. We had no idea how to do it. And there came this really beautiful paper of Russell. I'm not listing the co-authors, you can read them in each paper, where they basically solved this problem again with beautiful techniques. I vividly remember Jeff Edmonds' lecture in Stock, which was so exciting. So they proved it for universal relations. We still don't know if for, Boolean relations, which should imply circuit low bounds. And so at the time I was extremely optimistic we could, maybe use this to prove circuit low bounds. Of course, not much has happened since. Some has happened since in this direction. Another paper, which I really like, I want to talk about some joint work we did. This paper, which also regards communication complexity, really spells out or finds a different way to express Nissan's very famous seminal space-bounded generator. Noam used hash functions, and we found a way to express it using communication complexity and expander graphs. And I think this point of view was extremely useful to later developments. It's just, even though it's just a re-expression of Noam's generator, I think that maybe the first paper we wrote together, where we collaborated there, it's, I can tell many stories about Russell, maybe I'll tell one. Russell would visit Jerusalem to talk to Noam and myself. He visited several times. I was at the Hebrew University then. One day in Jerusalem, very late at night, I got a call from somebody says they work in the security, allow security in Prague. And there's a guy who says he's coming to visit me and wants to board a plane in Prague. Do I know who it is? I said, no, what's his name? And he said, I'm not telling you. How does he look like? I'm not telling you. You should know if you want this guy. Now, at the time, I think Russell probably coordinated this visit with Noam, and this was Prague, not the US. I had no idea what, and then I had, one of my, an insight of the type I rarely have. And I said, wait a minute. Does he look like a big red-haired guy who looks totally lost? And he said, that's exactly him. So they, it was Russell, I guess, right, and they let him on the plane, and maybe that's when we wrote this paper. Proof complexity. Russell wrote numerous papers on proof complexity as a key figure there, and I want to mention just a couple that I really like. The background is, of course, that the structure that Cook and Rachel suggested for doing complexity on proof system or propositional proof systems. One key paper is this paper of Russell, where until then, most propositional proof systems were logical, of the logical variety. They introduced the nostalgia proof system, and in general, algebraic proof systems. They asked and proved the lower bounds for them. They showed the lower bounds for algebraic systems, imply Boolean system lower bounds. There were techniques that influenced greatly further developments. Also later was a paper on the Grobner basis system. Anyway, it was a major development there to go into the algebra. Another paper I really like is this paper on the relative complexity of NP search problems, where basically, the Christos' the Papadimitriou classes, the famous PPA, PPAD, all these classes based on combinatorial principles were known, and they were described in terms of computational complexity, where the inputs are basically circuits. And what they do in this paper is put the whole thing in the framework of oppositional proof complexity, and in a beautiful way. All right, I guess I talked about 15 minutes, so it's good. I'll finish on time. It's not that it's important to finish, of course, because there is enough and more than enough to talk about, but let me move to different areas. Randomness extractors, the background here, one can find many sources to the birth of extractors. There's this really beautiful paper of Karl Pippiger-Zipser about how to amplify errors in probabilistic algorithms without any additional randomness using expanders. This was one of the first, important demonstrations of the power of expander graphs, already in '82. I was a student then. The famous Santa Vazirani paper on weak sources was another source, and the Isaac Conrad-Zemeredy paper on deterministic simulation of probabilistic log space with few random bits, all are sources of extractors. But I want to mention this paper that Russell wrote with David Zuckerman, How to Recycle Random Bits, as something I see as a key to the development of logarithmic seed extractors. They didn't have it there. They had an amazing idea of using what they proved, the leftover hash lemma that's extremely useful in lots of situations, and showed how to, how do you reduce errors with almost no additional randomness, and without explaining this happens in equal size blocks. And that was something that Zuckerman soon realized was not optimal. And then alone and with Noam Nissan, they realized you should look at, blocks that are going geometrically. And that led to the first of all, the clear full definition of extractors and, first construction of logarithmic seed extractors for, I guess, linear mean entropy, and everything started from there. Lots and lots of uses of randomness extractors. More. Okay, so yeah, I want to go to two papers I wrote with Russell that I think I really love. We already had the background here is that, well, of course, we knew of the cryptographic generators of Blam-Mikali and Yao, and then Noam and I came up with this so-called NW generator, and there were lots and lots and lots of progress on optimizing it, and it was still not optimal, and trying to find ways to make it uniform, like the BMW, Blam-Mikali and Yao generators. We couldn't do it. And then, Russell and I got to work on this. And one paper in 97, did the optimal, made it optimal. And just saying something about what's going on, there are two things there that I really like. One is that PRGs were all about fooling circuits or fooling probabilistic algorithms, and so on. We realized that you should also fool lemmas, in particular fool the XOR lemma in order to do it. And another idea was that XORing different PRGs sometimes works. It doesn't always work. It's like combining two crypto systems and XORing the output is not always a good idea, but in the context there, it works, and these are key to the proof. Then a year later, we handled the uniform case, so doing the randomization using the NW generator in a uniform context. This was really, a mystery, and we spent some time in the introduction to explain why 10 years were needed, at least for us, to be able to do it. And one key aspect, you need values of a function you assume is hard. Doesn't make sense. Where do you get it? It's hard. That was why it was hard to prove this theorem. And we realized then that, assuming a distinguisher to the generator we proposed is allowed learning values of the hard functions that can be useful. This is not true in general, but it works for the permanent, for example, or using a function which has both random self-reduction and downward self-reduction. This was absolutely key. And that's a powerful idea that was also used several times, but certainly in the seminal paper of Cabanes and Impagliazzo, which shows that de-randomizing PIT means proving lower bound. What else? Structure versus randomness. Okay, Russell, I very clearly, even today, remember his lecture in 1994 about this paper in Aarhus, where for some reason, lots and lots of complexity theorists gathered, mainly Israeli ones, gathered in Denmark, Aarhus in the summer of 94. And Russell gave this amazing talk about understanding, functions that are somewhat unpredictable. I should have put a picture to explain what he's doing, but those of you who think about, it was always a convenient way to think about a function, a coin which is biased 1 minus delta, let's say towards 1, as a sequence of 2 coin tosses. You toss a coin with probability 1 minus 2 delta being 1, and then with probability 2 delta, the remaining probability, you toss a fair coin. That means that, function, one way to generate a function that's 1 minus delta hard for a class of circuits is, maybe easy everywhere on a 1 minus 2 delta fraction of the inputs, and on 2 delta fraction, it's extremely hard. It's, algorithms cannot tell it apart from a random bit. What Russell proves here is that this is the only case a function can be somewhat biased, 1 minus delta bias. That's the only way. And this led, it didn't just lead, I must say, there are independent works, but it's part of the understanding of what we call today structure versus randomness paradigm that's extremely powerful, both in complexity theory and in mathematics. It appears independently in the Green-Tau work on the arithmetic progressions in primes, in the dense model theorem, and Tulsiani, Trevisan, and Vadan extended all these works, made them more efficient. It's a beautiful development and absolutely fundamental. Maybe that's the last one, so I'll let you be soon. Again, typical Russell. We are also, at the time, so ingrained with the polynomial time reductions, and then this paper came, and that, we should look at other notions of reduction. How about sub-exponential reduction? This paper has lots of great things. One is, well, you probably know that sunflowers entered the TCS scene in 1985 when Razborov proved this, monotone circuit superpolynomial lower bound. And in this paper, it enters in a far, far more sophisticated way in order to define, new complexity classes and new assumptions stronger than P different than NP, like the exponential time hypothesis and others. And the need to generate complete problems for these classes. You need sunflowers. Let me not try to explain it here. It's just, you should read this beautiful analysis proving that K-sat with a linear number of clauses is complete under sub-exponential reduction. This is absolutely beautiful. Great conjectures there. We don't know how to approach them yet. Of course, many years later, this was absolutely key to the development of a field that I'm sure Ryan and others will talk about, what we call today fine-grained complexity, understanding polynomial time complexity, exactly which polynomials are needed, what's the best algorithm for polynomially solvable problems. Okay, my time is up. Russell and everybody, Russell, happy birthday and party. It's really late here. I'm not sure I'll stay for much, but I wish you a happy birthday, many happy returns, all the fun you can have.